Hi everyone. In today's episode, guest is Professor Reimund Rötter. He's a distinguished researcher and professor at the University of Göttingen with over 25 years of expertise in agronomy, agricultural systems modeling, and agroecology across Europe, Africa, and Asia. Professor Rötter's work focuses on developing and identifying solutions to the complex challenges presented to humanity, such as global food security, increasing resource scarcity, and the environmental effects of agricultural production under current changing climate. He has done substantial work on his research area, and if I start naming them, of course, we will run out of time. But mainly impactful contribution include research work on genetic yield gap, modeling the multifunctionality of landscape, and assessing agricultural impacts and adaptations to climate change. Notably, his work on the reduction of global wheat production under rising temperature as well is also very interesting. This also makes Professor Rötter a perfect fit into today's podcast on discussing crop modeling and its impact on addressing climate change. Welcome, Professor Rötter. Thank you for being here today.
Thank you, Nazia. Thanks very much for this nice introduction.
Yes. So I want to start from the beginning. What is a model? And for a scientist who have no understanding of statistics or data science, what is the most common misconception about models? Or it could be crop models, climate models in general.
Mm-hmm. Yeah, more generally, you could say a model is a simplified representation of a system. And the biggest misconception is then about models, whether they are climate models or crop models, that they are accurate representations of the real world. And so that we can simulate or reproduce the real world system exactly. But that is not usually the case because, as we said, models are simplifications and they have also been developed for different purposes. Yeah, so they have a certain angle, what they are supposed to address. So you can have 5 crop models and each one could have been developed for a different purpose. Not all for predicting yield, but maybe some for simulating the crop water balance. And that makes them different. Yeah. And that is something, that would be the first thing I would say.
Also, when I was preparing for this interview, because, I'm very enthusiastic about the model is now one of the hottest topics, let's say, and also research area as well. Everyone wants to bring modeling into their research and somehow have it in their research. And I came across with this statement: no modeling without experimentation and no experimentation without modeling. What do you mean by this statement?
Yeah, maybe I still would like to add something on the previous question, because maybe it was a little bit too general.
Yes, of course.
When I say models for different purposes, so I should have given some example also. There is, first of all, that you can have an agroecosystem model and you emphasize more on the soil or more on the above ground part, or then more simply on the water relations between atmosphere, soil, and crop. Or then you can also have different type of purposes where the model is going to be used for. Like the one could be just, as we are in science, to test hypotheses. Yeah, to test different kind of hypotheses. And because a model is a kind of formalization, formalized knowledge, and it has distilled knowledge in it. Of course, with that one, if it has been well tested, you can then also test hypotheses. But you can also use it for self-education to learn about interactions between subsystems and interrelated elements in the system. Or then you can use it for decision support. So this is just to say there are different types of models for very different purposes. And coming now to your later question, when you mentioned you found something about models that said, how was it again? No modeling without experimentation, right?
And yes, and no experimentation without modeling.
Okay. So actually, this statement goes back to the father of simulation modeling. The first part of the statement goes back to Kees de Wit from Wageningen, who founded the Wageningen School on simulation modeling. And he said from him is then no modeling without experimentation, because after you conceptualize a model, you say for what purpose you use it, what basic data you need, then is the time to test it, to parameterize it, to calibrate it, to validate it with new data sets, to really make it see whether it's fit for the purpose. That is this part. To say no modeling without experimentation. You need experimental data to calibrate, validate, or verify and test it and evaluate it. The second part is, I remember that was in a discussion I had, for instance, with Sandra Aseng 6-7 years ago. So no experimentation without modeling. That means if we have well-tested a model that is fit for its purpose, that can describe the major processes in an agroecosystem, for example, the interrelations between soil, above ground processes, atmospheric processes, then if we say, yes, it is fit for the purpose, then we can use it also to detect where we have knowledge gaps. So when we run it and we analyze the different outputs, that's, by the way, the definition of simulation, the art of building mathematical models and testing their properties in reference to real world situation. So if we do this crucial step of simulation and we compare to real world situation, then of course we will find that the model does not always give right answers or shows a gap between the model and the reality. And exactly at those points where we find the deviations between what is modeled or simulated and the real world, there is where we start to dig deeper. And often it brings us to a point where we say, here we have a knowledge gap. There are simply too few data available. Yeah. So, and of course, if there are not sufficiently data available, I give you an example. For instance, we did a review recently to see whether there is sufficient data, experimental data, between interactions of different abiotic and biotic stresses. Already for the abiotic stress interaction, if you look at drought and heat for specific crop systems, you find very little experimental data, very, very few empirical data. So that means simply, how can a model then capture realistically the impact of concurrent drought and heat, for example? Yeah, if you have very scarce data. So that is exactly where we find deviations. We dig deeper and we look at the situation and we find, oh, hey, here we have an enormous gap of knowledge. And then we can specifically address and design experimentation or experiments, field experiments or in the lab that fill exactly this knowledge gap. So that is, the modeling can help us to guide us to make proper and much needed experiments.
So basically, to have a good, reliable model, we must have good data. It's as rubbish in, rubbish out. Or
that applies to everything. If we look at different models, you mentioned already crop models or agroecosystem models, climate model. It applies to all these models. Also for climate models, if you don't have, for instance, data about the humidity and temperature in higher atmosphere or troposphere, and if you have an imbalanced amount of data, like you may have a lot for temperate regions or for for Asia, but nothing on Africa. Of course, in the end, the climate models you develop, the numerical climate models you develop, will not be balanced, and they will have shortcomings. Mm-hmm. So it's, or if you want to test a model and you don't have a time series of data, how the humidity in the different layers of the troposphere have changed, or the temperature. If you don't have time series on that, then also you cannot test. So and the most simple, maybe for us, whether soil scientists or geoscientists or who have working with spatial data, with maps. Of course, a map is a model. And if you don't have exact information about whether it's a soil map, if you don't have enough auger points, you will have uncertainties in the map.
Mm-hmm. So as I understood, before feeding the data into the model, we should first quality check the data.
Even also that, yes, that is an important step. So usually after we have conceptualized the model and checked whether the major processes are captured for the purpose it is developed, and we have gathered the data, then usually what we do is we use the more comprehensive data to calibrate them. To calibrate them for instance, a few points and see how they behave vis-a-vis the real world. Different kinds of outputs, not only yields or biomass, but also water use and other outputs of the production process. And we have really comprehensive data sets to check whether the model does not only produce a good end results, but also dynamically during the growing season. It produces the right leaf area, it produces the right diameter increase. Then, when we have verified that, or we have calibrated well, then it's not over yet. Then we have to go to other situations. Then we have to see whether with less data, we can also, in other situations, with other soils, with other weather conditions, the model still works for purpose, what it is meant for. It's a whole loop of testing and checking and possibly in between improving. Yeah, if we find there is something not well formulated, till you have a model that you say this is robust, this is reliable, it can be used.
Yeah, I'm sure that there are a lot of things that you will remember later you want to mention, but I guess in the next questions, if you remember, you can also note as well about modeling. But I wanted to know, so the data is the main requirement, data quality. What are the other requirements to build a reliable model?
Well, of course, that's what I already partly said in my answer. First of all, of course, you have to say for what purpose you want to use a model and with what accuracy, for instance, you want to have the results. Whether is it a crop model to estimate how the potential for food production is on the whole globe or in Africa? Or do you want to have a model that can advise the farmer what kind of nitrogen application to apply on his field and even in the different corners of his field, taking into account heterogeneity? So these are completely different questions, and in the end, you will come up with very different models. And depending on the purpose, you select the main processes that you want to include. So if you have a kind of global model, you will include less processes than for a very detailed application like in precision farming, something that you are involved in. Yeah.
Yes.
So that is the whole. So the conceptual model that is as important, if not more important, than the data. But it is very difficult to say. Of course, both is important to have the right data at the right quality. But first, also to have a model which contains those processes that are absolutely necessary. And it's also maybe, again, an analogy with cartography or making maps. After you have decided what components or what processes or what parts you include and for what purpose, then you simplify. You can generalize in various ways. A map, you can generalize. You can put something, emphasize something more and put other things away. Or then, you have to generalize and to simplify at a certain point.
Mm-hmm. So the modeling, as I said before, everyone, of course, we all want to bring it into our research and somehow model and simulate the results and see before we test it in the field. And this, we have been relying on model for almost long time. But when we needed the most, especially in COVID-19 breakout, most of the models, that they failed to predict forecasting for COVID-19, even though the results were accepted by the policymakers. So what are your thoughts on this? Why models failed?
Well, I would first say, of course, the COVID pandemic, in its form as it occurred to us, has been a very rare, if not a unique event, in this dimension. And I think if you remember when the first reports came that there was something happening in China, we all thought this is very far away. I remember I was at the crop modeling conference in Montpellier in February 2020, and we looked around, who is from China, But then nobody had any idea that it would spread so fast. And I think COVID is something that you can a little bit compare with extreme weather statistics. So the extremes, of course, happen in the tails of the distribution function. And there they are by definition rare events, and handling them and predicting them is, of course, much more difficult than something that is more common, like a normal growth development processes, yield formation, transpiration. There we have our physical principles that we think we understand pretty well, and we can put them together with good data of soil and weather and crop parameters and properties. But for these kind of rare events, which even in the beginning, the properties of the COVID virus was not known. It took a while to find out what it actually it's like and what its nature is. And then, of course, one could little by little start to think about prevention. So this is something very rare. Of course, on the other hand, of course, there had to be people who had to start and do the modeling to look at potential consequences. But this is something that I compare more with these synoptic weather models, that we have. You need starting conditions, and then the prediction can be quite well if you make the right assumptions at the start and give the right data at the starting conditions. It's not comparable with agroecosystems model, which really works on ecophysiological principles, and then is, of course, also dependent on the quality of the field data as much as we are dependent on the quality of field data when we do field experiments, when we do not computer experiments, but field experiments. Also there we have, of course, our errors and uncertainties in the data. So
exactly.
So I think this COVID model, was quite a challenge.
Yes, as well. We were all, I guess, as a society, were unprepared, and everyone was panicking as well. And society, it's hard to predict actually what the individual person might behave.
Yes, and that is, of course, then because you mentioned also when you talked to me, you mentioned crop models, climate models. Of course, the global climate models they are numerical models of the interactions of the ocean, the atmosphere, but then they are driven by emission scenarios. And the emission scenario is there the big unknown. We can only look if we have a certain narrative that leads to a certain emission scenarios for the future, then we can feed that into the climate model and say, look, if this would be true, what would be the content? But you cannot expect from any climate model to give a prediction. That's out.
Mm-hmm.
Climate models, they cannot predict. They can make a projection. They can look at the consequences of certain assumptions. So what if this set of emission scenarios is right, and assume the interrelations that I have included into my climate model to simulate the impact on the climate system. If I have included all important processes there, then we come close to what is likely to happen.
Mm-hmm.
The climate model, you have these two components. As you said, there comes the societal or the behavioral component.
Yes, exactly. Yeah.
Which is very hard, if not impossible, to predict, and we don't know now. Of course, you see what's happening in Europe. I see what's happening in Germany. There's a government that has been very ambitious to try to implement climate policies, but they are also behind their targets, even though they try massively. But of course, there come other factors in that disturb the ambitious plans as we experience right now.
Yeah, exactly. Because it comes down again to society, and as a society and as an individual, it's hard to predict of course, there is a behaviorism, a science that predicts the certain patterns of human behavior, but as a society, as a group, it's hard to predict, I guess. Yeah. As well, I guess this next question is a summary of your overall work in your research area, in your research career. And I guess here you could broad up more and explain more. So how does crop modeling contribute to tackling key challenges in the agricultural sector, such as food security, nutrient management, climate change, and yield improvement? And what makes crop modeling so crucial in addressing these challenges than, traditional field or pot experiments?
Yeah. So of course, if conditions are changing, be it environmental conditions, so climate, soil, or be it also changes in technology, which happen all the time, this has impacts on the outcome of our production systems. And even then, if we change the production systems or the properties of the systems themselves by breeding, for instance, we will have different outcomes. We will have new constellations, things that have not been there before. And always when it is about the future, when we do not look to the past, but we look into the future, we need some kind of models. That is simply the task of models. Yeah.
Mm-hmm.
And what the models try is to put the knowledge that we have firmly, to put that in some kind of equations, mathematical equations, if we have process-based models, and to describe the main interactions of the interrelated elements such that it is reproducible. Yeah. And if these models can reproduce something what happened in the past, then we have confidence that it also would be able to allow us computer experiments of new combinations in the future, which otherwise would be too costly to do in the field. Yeah, and it would take too long. Yeah. So if we want to have all combinations of possible application rates and timings in combination with the different soil and climatic conditions now and in the future, how are we going to do that? It's impossible by conventional experimentation. So for these cases one needs model. And of course, in terms of the climate model themselves, to look at future climate projections, of course, it is self-evident. Otherwise we cannot know. And so you have to see crop models as a kind of part in the chain. Like if you want to project the future in terms of climate, then you use climate models, and then the crop models would be the impact models that would look at the crop or cropping systems part. You have livestock models. If you look at the big networks that we have developed in the last 10 to 15 years, like AgMIP, and we also had Maxur for Europe. So big networks that want to intercompare and improve agricultural systems models. Then you see there are different groups that work on different models and different components. So like trade models, world trade models, to look at the effects of changes in yield, on food prices, on consumption, on land use change, and so on. Yeah, and you have livestock models that would purely look at the livestock sector, and then you have a coupling also of the models, the so-called integrated models, to really then look at future food security, like the early studies of Cynthia Rosenzweig. And nowadays, we have them in AgMIP, and you find them in the IPCC reports of Working Group 2. So simply when it comes to the future and we want to say something about the future, then we need these models. But it goes further, of course, that with the help of these models, we can, of course, guide also very much management decisions in the here and now, if we have found them reliable and robust. Yeah. For instance, if a model that includes all the processes important in nitrogen dynamics, the uptake, the mineralization, the movement between the labile and the stabile pool, all these. If it is well developed for a certain climate region and a certain soil and cropping system, then you can, of course, use it to optimize a fertilizer application.
That's directly on point on my current research. Yes. Yes. You've mentioned about future trends. Of course, the modelings are a perfect tool for predicting the future trends. So as well, in your works, you've also have done related works for the future predictions. And what do we know so far about future trends in agricultural production, according to model outputs?
What normally is done, one looks first of all, what would happen if the changes in climate and the atmospheric CO2 impact on the as they are, without any management changes. This is usually the first step, what we call then potential impacts. And that means we take the output of climate models, feed them into the impact models, into our crop or agroecosystem models. We also implement the certain changes in the atmospheric CO2, depends on the crop type, whether they are a C3 crops, so with the C3 photosynthetic pathway, or C4 crops with C4 photosynthetic pathway. They react differently on CO2, atmospheric CO2 and elevation of atmospheric CO2. And then we look what would be the outcome on biomass production, yield, and phenology, possibly also water. Then what the big trends, if you do that, would be that wheat production in Europe, but also for most of the globe, would increase under future climate change. Yeah. And this is simply taking the relatively simplistic climate change scenarios that the current generation of climate models can produce. And they would predict an increase in temperature. They would say, okay, you have higher CO2, 2050, you could have 480 or 540 ppm, depending on the on the emission scenario, and that would be an enormous CO2 fertilization effect for C3 crops like barley, wheat, oats, etc. However, for maize, you would have a reduction in yield, because there, first of all, the CO2 fertilization effect wouldn't come into power. It is the C4 crops are already CO2 saturated. It would only slightly gain for an improvement in water use efficiency. Overall, most climate projections would tell us that potential impact on maize yields would be negative. A typical study that reports that is Jägermeier 2021. It's a kind of follow-up to the IPCC report. But then comes the next step. Of course, that is not the end of the story, because farmers at all times have adjusted to changes in climate. Another thing I haven't said yet also is that this conventional output of global climate models or regional climate models do not fully reflect the changes that we have in extreme events. They are not yet able to do that, especially not, they cannot tell us how much the interannual variability of precipitation or temperature will increase or decrease. They are very poor in that. And we have to be aware of that.
Mm-hmm.
We take then other techniques. We look then how much has in certain regions already variability of precipitation and temperature change, interannual variability during the growing season. Then we can use so-called stochastic weather generators to change the statistical parameters such to reflect our assumptions on how variability is likely to change. This is on top. This cannot be an output of the global climate models. They don't manage that. So you see that is an important component. And we are then at the moment where we say, if we see the potential impacts, then comes the part where we then react by adaptation. At the adaptation, we have a very broad range of possible adaptations. Of course, the farmers, they react by changing the sowing date, moving earlier or later, depending how that movement would more or less expose the crop to stresses, to heat, to drought, or to flooding. So that has to be found out, and we can find it out with our crop models. We can see if we move earlier or move later, whether we get more exposed to those stresses or not. So we can anticipate. And then we can say, okay, the optimal sowing would be 20 days earlier. Then the farmer has, of course, and always has done so, they can make cultivar choice. They can then choose a cultivar that either takes advantage of the improving conditions, then you would taking, for instance, a later maturing cultivar, because at that situation, that crop would not expose so much to stresses anymore because rainfall has increased, there's higher CO2 and so on, and it has become warmer. Yeah. And he would then, with the sowing and the cultivar choice, he would try to exploit the new situation. In another situation, let's say in the Mediterranean, it could be that it has become much more warmer, hotter, and also much more drier. So you rather would choose a situation where you optimize sowing and cultivar together, so to avoid any exposure to severe stresses. Yeah. But then we are only with sowing and with the crop cultivar. Then we have not even gone to future breeding. So the next step would be, one would check at the situation, can we supplement water by supplementary irrigation? So if we have dry spells, maybe they are not so heavy. Do we have the water available also in the future? So is supplementary irrigation an option? Yeah. So we combine a couple of adaptation mean, and the combination of those could mean a real adaptation and mean the impact of climate change could be either minimized or even the other way around. We could get a yield increase in the new situation by new interventions, management interventions, and combinations of crop and soil.
Mhm.
Now, if once we have that, then we could say, okay, this is what we can achieve with incremental adaptation. We can partly reverse this potential decline of yields. We can maybe sometimes even turn it around. But then, if we look, where do these adaptations, these relatively favorable or cheap adaptations, where do they not help? There we might come in and might say, oh, now there is a task for breeding, because all of the wheat cultivars for this part of Europe, or for Europe as a whole, they will not help. We have so severe heat and drought stress, combined maybe with some new pest and disease pressures, that we need new cultivars. Then breeding comes in. And there is also a whole range of possibilities that we have to target our breeding for certain new environment. And for all this, you need to be able to show what future environments there are likely to come and how they will likely affect a certain system, cropping system that you have in mind. And that for that we need models. And then such studies, such kind of computer experiments, they can directly guide breeding programs. They can, for instance, with a model, you could say, in our model, this combinations of traits would be optimal to overcome the upcoming severe drought stress concurrent with heat waves, because these are traits that would be tolerant of such conditions. And then the breeder would look, and he would check on the gene pool and do crosses with different kind of advanced breeding tools to come then to new breeds that can face the situation.
Wouldn't it bring then, because we would be, due to the severe changes in the climate, drought, temperature rise, and intense rainfall, wouldn't it, of course, we would rely more on stress-resistant species. But then wouldn't it pose the threat of having only few species that would be very susceptible? Because if also via evolution, pests and insects, they also evolve being resistant. And if we have some sort, you know what happened to banana species that in South America?
Yeah. I see, of course, there are different approaches. I mean, I only mentioned now one pathway that where our conventional adaptations or incremental adaptations wouldn't work, that then breeding is challenged, or plant breeders are challenged. But of course, and that you also see in the last IPCC report, AR6, working group 2, that apart from risk avoidance or risk minimization, so adaptation and mitigation, of course, you want to create agricultural systems that are more resilient than the current ones. And resilience can be introduced in many different ways. Of course, it depends always on the level that you look at. Also, there, of course, models can help a lot. One way is, of course, that the most obvious ones at all times has been diversification of your activities, to make yourself not relying too much on one single production.
Yes, exactly. Yeah.
But you look at several, and there have been also in the last 10, 15 years approaches that have said we can manage risks by introducing response diversity. Response diversity is a concept that has been developed. For instance, we have a project in Finland where we look how can you increase response diversity of barley production if you introduce different cultivars that have tolerances to different kinds of stresses. Because the starting point there is that you say, I never will be able to predict with high accuracy how the future will look like. There can be heat and drought, but at the same time, the risk of flooding is not avoided. So you include the mix either of different genotypes of barley, or then you diversify your farm. You have different activities, so to make yourself not relying too much.
Okay. And can climate change itself impact the quality of model predictions in the future? Because as you know, I always ask people, local people in Göttingen or in Ghent here, I ask them, how did winter look like when you were a kid? And their response is, of course, very appalling. They had snow, they didn't have this much severe seasons, or summer gets very heated up, or the season is changing unpredictably. So as long as this is happening, we are collecting data under increasing patterns, changing patterns of frequencies in the rainfall and also in the temperature, and how this will impact the quality of the predictions.
Then my first answer would be, no, it doesn't impact. If you ask your question as you did it. So can you repeat once more?
Yes. Can climate change impact the quality of model predictions?
If you mean as model predictions, the predictions of a crop model? No.
Even under, what I mean is currently climate change is already happening. It's we say it seems as future because we talk it as in the future, in a severe case when there is no turning point. But at the moment we see that the season is changing, and even I had a situation where my seeding was fertilization date was postponed for 1 month almost, where it had to be 1 month early, typically. So, but this data, we are collecting this data. We are making experiments with seasonal changes, and their rainfall patterns are changing. But if we feed this data to a model that we want to predict the future trends, wouldn't it be somehow impacted?
I don't see it that way. I rather see that, of course, that we see already now a lot of changes, that the climate system already reacts differently than, let's say, what we knew 10 or 20 years ago. That we have, like, if you look here in Germany, I was recently talking to breeders, and they had 3 years experiments, and they say, not a single of this year was a normal year. So all were exceptional. Either it was much too dry, or it was too wet, or there was a weird combination of dryness and wetness.
Yes, exactly.
So this is, of course, something that if we try then to reproduce that, of course, and if we measure this, if we now closely monitor these changing conditions, that provides a new set of data, of course. So which we didn't have before. And that is also a point that I made more than 10 years ago, that most of these crop simulation models that have been developed or around and widely applied in climate change impacts on adaptation assessment, they have been developed from experimental data from the 70s, 80s, or early 90s. So situations where we never had these extreme high temperature or combined heat waves with high temperature. So, of course, we need new data sets to make the models more fit. But we do not only rely on field experiments. Of course, we can design field experiments with rain-out shelters, for instance, with thermal towers for warming in the field. We have all kinds of devices where we can create new controlled environments. Of course, in the extreme case, in big climate chambers, that we can study the combination of elevated CO2 and drought and heat under very controlled conditions, unfortunately, only in pots. And that is, of course, that means in the end, we can get a number of positive hints or good insights, but anyhow, we need to go out into the field and test it there under real world conditions with a real root zone and exposed to also to other factors. But there is a lot of, in stock that we can utilize to reproduce these new conditions. And as you say, if I understand your question, of course, if you utilize and closely monitor what's happening and do that not only above ground over the season sequentially, but also below ground, then of course you get new data sets that improve our models enormously and make them even more powerful than they are now.
Yes, in the last point, you said even make it more powerful. You've been working with crop modeling area over 25 years. And AI, we should all admit, is the hot topic. And does AI bring new solutions into modeling, crop modeling, specifically into agriculture? Have you noticed it?
Yeah, of course, if we talk about crop models, to be complete, I should have said what we are mostly using are these process-based crop simulation models, are largely deterministic. Yeah, so we explain causes by certain effects, by certain factors. But then, of course, we have data-driven approaches. We have also empirical models, statistical empirical models. They completely depend on the quality of the data. They don't care about principles, or they don't try to explain what is the effect of what and what's behind it. But the combination of both, we have hybrid models where we try to combine data-driven approaches with process-based models. And I think that is, of course, that's what we will see in the future, what you already see in papers appearing, testing out to what extent can the combination of data-driven approaches with process-based models improve the robustness, the accuracy of predictions or projections. That's certainly coming. And of course, ChatGPT offers an enormous dimension to us. We will have our own agents, as Bill Gates recently formulated it. And if I remember correctly, the abbreviation stands for Generative Pre-trained Transformer. Yeah, this is ChatGPT. And of course, with that one, the pre-train is the keyword here. It depends to what extent we will be able to provide very good quality data sets to train these agents. That is the key. If we just let ChatGPT look on the internet and see what's out there without any filter by experts, by us, it will come up. Yeah, it always come up with solutions, but we can't say anything about the quality. And I have been sometimes for fun, telling my son, he is in the IT business, and I said, can you ask these questions to but I didn't have it yet on my, I said, for instance, look for the best model for simulating nitrate leaching on a loess soil in the Rhine basin. And then you get a very, very vague general answer. You have not anything out of it. So it depends completely how you train, not to ask these simple, trivial questions, but ask very concrete questions. And then, of course, you have enormous opportunities. For instance, if we were able, and I don't know why that is not possible in Germany, if we would have very good digital soil map, high resolution soil maps, it should be possible. I mean, you have seen the one for Africa by ISDA. They have a 30-meter pixel soil map for Africa using artificial intelligence techniques, among others. But we don't have it for Germany. So if you would have that, and then you have your monitoring of your season conditions, and you have nowadays sensors for temperature, for humidity, they are all cheap. Weather stations are relatively cheap. So if you, for your field, you compile all these situations and you make it then available and you train these transformers with your data, then of course you can use your iPhone. You can ask all kind of questions. Which field requires nitrogen urgently, for instance? Or you say, how much yield do I lose if I plant this hedgerow? If you have trained your agent with your own data that you have generated, which is also, I think that is, of course, possibly your next question if you combine all the different digital tools with drones, with remote sensing data, which are also very high resolution nowadays. If you combine all that, and if you make that available to train these agents, then we are in a new world. Then we are in a revolutionized agricultural world.
As an academic research, you are more welcoming to these new changes.
Well, I'm an optimist. I always believe that the good forces of humankind come through and make it possible to select the good and separate it from the bad, or let's say the valuable things from the invaluable or dangerous or deleterious things. I tend to disbelieve, although sometimes history has shown us the opposite. But I think, of course, we know that artificial intelligence has a lot of downsides, and we have to look at them. But these are, as you started, these are then more societal again. That you say, if this comes, if we will be able to utilize artificial intelligence and make farming much more precise, we get much more information on time as we need it, and thereby can optimize. Use our inputs more efficiently and also so that they are more environmentally friendly. Then we have to look what are the downsides, at what cost does it come. And of course, I think we are not yet in a position. I think with developments in artificial intelligence, for instance, as Bill Gates describes them, that in 5 years' time, we will completely work differently because of this rapid development of artificial intelligence. And I see already how much better this ChatGPT becomes every week. So
every day.
Every day you could say. And then, of course, we need to start to think what kind of data exactly for agricultural systems now do we have to collect, and then who controls the data is the big question. And then we need to define standards for quality. So there is a whole range of new tasks that comes to us. And I think, especially for your generation, you have to find answers to this. Who who makes the models, who controls the models, who evaluates the models that become then possible to combine data-driven and more conventional process-based approaches. So many questions.
Yes, but
Do we,
as
do we have the skills as agricultural scientists? Do we completely have to change our teaching programs, or let's say to reform and have other courses, create modules that prepare us to embrace these new developments? There are so many questions. And last but not least is, of course, it, as in science more generally, the big breakthroughs or the big progress comes through collaboration, collaboration across disciplines or across boundaries of interest groups, of stakeholders. So this kind of collaboration across disciplines, but also across different users and between public and private, how we organize that. I think that will be key on whether we make benefit from it, or whether in the end many people lose because of it.
Mm-hmm. Any advice for young researchers entering the academic world?
Yeah, that is again, of course, such a question that it depends on how the academic research system is going to develop. I have considered it in the last 30 years relatively stiff. It hasn't changed so much. So if you look for young researcher, if you really are interested in an academic career, you are somewhat forced to specialize and specialize very deep and make profile dig as deep as possible. And for people like you, I guess, who like to see the broad picture, may that be disappointing that you have to dive into very deep. Like a good colleague from Wageningen, Johann Baumer, he once called it T-shape. So, and you need to go deep, this vertical line, and then you have to, make yourself known by this special niche that you are very good in. That also allows you to collect the publications, which are still the currency of academics. Yeah, the publications and of course the external funding that you generate. These are the currency, and only then, when you have then collected a certain minimum number of publications, then you can start and you can move up, and later in your career you can get broader and broader and broader and connect to all those fields that you always wanted to do and wanted to include. But I think in the current system, you are still forced to cover a very specific area and show, here I'm the best, and then do as much as possible, exploit that, follow that line, collect your publications that, especially in young years, like, in the first 5 or 6 years after your PhD in Germany, you get all kind of offers. There are all kind of programs for young career researchers, but you have to have shown proof that you can publish and that you can also present. So go to conferences, present there your oral presentations. This is, it could be otherwise. Of course, impact is as important, or maybe in the end more important. The impact of our science matters. But as a young researcher, you are forced to go that way, and then finally create impact. And then you will have more impact. You will get access to all these gremia and all these, let's say, decision level where you then can really have impact. And without a doctorate, you will not have it, and also you will not further march further in the academic career. So don't forget there is a T-shape. Don't forget the big picture. try always to connect what you do there deep down. Try to connect it to the big question, but you cannot spend the time to handling the big questions before you have not proven that you can work according to the scientific method and also produce output.
Okay. Thank you very much. Thank you very much for sharing and with your insights on today's topic, as well on giving personal advice on the last question. I hope the listeners enjoyed it very, very much. And yes, thank you.
Thank you very much. It was a pleasure. Thanks.
Thank you.